talk that I'm going to give is based on a joint work with my former PhD students, Ashita Kesarwani and Rahul Kumar, and this just appeared on archive on Ramanujan's birthday last year, 22nd of December. So here's the outline of my talk. So the series, the Lambert series that I'll be considering is involving this function sigma sub a of n. What is it? You take all of the divisors of n and then you raise them to 8th power, where a is any complex number, and you add all of those powers. Okay, that's nothing but sigma sub a of n. So I'll talk about this Lambert series, its historical background and its applications. Then I'll talk about a generalization of a modified Bessel function which is instrumental in this regard. I then want to go over a master identity which we found, which gives numerous very well-known results as well as new results as special cases. And finally, I will say something about a transformation formula involving this Rk of n function. Rk of n is nothing but you take any positive integer n and look at the number of ways you can write n as sum of k square. Okay, so I'll come to that, and that requires some use of certain kernel, which I will go into appropriate details depending upon how much time we have. Okay, so let me start with the definition of modular form. A modular form is a function living on upper half plane. So the domain is upper half plane, and it takes any complex number as value. So it's function from upper half plane to C. It is said to be of weight k on SL to Z, which is nothing but the special linear group of 2 cross 2 matrices with determinant equal to 1. Okay, so it is a function on the upper half plane with the following 3 properties. F has to be a holomorphic function on H. F satisfies this beautiful transformation formula. So you take any SL to Z, any matrix in SL to Z, and then you take. So may I request all to please mute. If you have any questions, please you can ask me. But otherwise, if you could mute, then that will be nice. Okay. So there is this transformation formula. Professor Dilip, can you make that announcement?
Yes, sir. I am just trying.
Okay. So F satisfies the beautiful transformation formula. You take any matrix in SL to Z, and if you act on upper half, if that means SL to Z acts on H, then you get this AZ plus B upon CZ plus D, fractional linear transformation, and if F you evaluate at AZ plus B over CZ plus D, what is some factor, you get back F of Z. Mr. Shakir Hussain, could you please mute yourself? Yeah, thank you. So you get this transformation, and the third property is that F has to be holomorphic at infinity. Infinity is taken into the positive imaginary direction. Okay. So this is the definition of modular form. It is something really very important. There is one quote which is attributed to Martin Eichler, which says that there are 5 fundamental operations of mathematics. There is addition, subtraction, multiplication, division, and modular forms. So you can see from there how instrumental modular forms are in mathematics. A classical example of modular forms is the Eisenstein series E sub k of Z, where k is an even positive integer greater than 2, defined by means of this infinite series. So here zeta of S is the Riemann zeta function, the famous Riemann zeta function, and this factor is just for normalization purpose, but essentially you are considering this Lambert series, okay, consisting of this sigma sub a of function, which actually I defined on the previous slide. So you can easily write down this this series in this alternate form, and it's just using the definition of sigma sub a of n, which I said before. You take all of the 8th powers of all of the divisors of D, all of the divisors of n, and add those. Okay, so you'll get a double sum, and then you interchange the order of summation, and you are able to write one of the sums as 1 upon e to the ny minus 1. So it's very simple to derive this. When a is equal to 2n plus 1, okay, and when y is equal to minus 2 pi I z. So now let us see what are the conditions on our parameters. So a is any complex number, and y is in the right half plane. The real part of y is positive. Okay, so when I'm looking at y equal to minus 2 pi I z, I'm taking z to be in the upper half plane. Okay, you know, when I multiply any point on the upper half plane by minus I, I'm going to get something in the right half plane. Okay, so we can go back and forth between the upper half plane and the right half plane. When people work in modular forms, they always like to have the variable put in the upper half plane, but otherwise it's okay to even look at the right half plane with appropriate condition, real part of y greater than 0. So when A is 2m plus 1 in this particular case, either of the above series essentially represents the Eisenstein series of weight 2m plus 2. Because you see, when you have Eisenstein series of weight 2m plus 2, by definition, if I go back, when you have here k being 2m plus 2, here you will have sigmas of 2m plus 1 because it's k minus 1, right? So that's what I was saying here. Then A is 2m plus 1 here, then it is essentially giving you the Eisenstein series of weight 2m plus 2. When A is minus 2m minus 1, where m is a natural number, that series is representing what is called as an Eichler integral corresponding to the Eisenstein series of weight 2m plus 2. So what is an Eichler integral? You take the Eisenstein series of weight, let's say 2m plus 2, it will be the 2m plus first primitive of this Eisenstein series. So that is what is called as an Eichler integral. If you put A is equal to 1, when you get to quasi-modular form E2, E2 is not a modular form actually, we will see this in some details later. Mr. Suresh, is it possible to mute yourself? Yeah. Okay, thank you. Kumar, can you please request him or can you mute?
Yes, sir. I am just muting that.
Okay, thank you. If you take A equal to minus 1, then this series is what appears to be in the transformation formula of the log of Dirichlet eta function. Again, it's the half integral weight modular form. I won't go into much detail. Now let me actually discuss a very famous formula of Ramanujan. It's given in his notebooks. It's also given in his lost notebook. So this is a beautiful formula for odd zeta values, which means you are taking the Riemann zeta function zeta of s, which is defined for real part of s greater than 1 by the absolutely and uniformly convergent series summation 1 upon n raised to power s, and you are evaluating s. You are taking s to be 2m plus 1. Okay, so that is what is zeta of 2m plus 1. So you see a beautiful symmetry where alpha and beta are two numbers which are having their product as pi square, and m is any non-zero integer. So we have this beautiful symmetry here. Bk are the Bernoulli polynomials. So the history implications as well as modern interpretations of this formula you can find in an article by Bruce Berendt and Armin Straub. This formula has been instrumental in encapsulating the properties of modular forms and Eichler integrals that I'll discuss very soon. So first of all, we have seen that when A is an odd integer, whether it is a positive odd integer or a negative odd integer, this particular series satisfies a nice transformation and hence plays a role in the theory of modular forms. Basically, when A is a positive odd integer, it corresponds to Eisenstein series, and when it is a negative odd integer, it corresponds to the corresponding Eichler integral of Eisenstein series. But in the literature, there is nothing for A being an even integer except when A is equal to 0. So that is one of the goals of our work, in order to obtain explicit transformations for something like sigmas of 2 of n or sigmas of 2m of n in general, or sigmas of minus 4 of n. Are there no results for such series? So there are results, but they are not quite explicit. For example, Andrew Geenan, he studied this particular series, sigmas of 2k of n e raised to minus ny, for k any real number such that k plus half is not an integer. Now see, if you want k plus half to be an integer, what sort of k you should be looking at? 1/2 times an odd integer, right? And if that is the case, then what will be 2k? 2k will become an odd integer. Okay, for odd integer, you already have these nice transformations coming from modular forms. Hence, let us first consider sigmas of 2k of n where k plus half is not an integer. So you're actually looking at not odd integers anymore. What did Geenan do? He actually obtained a transformation for the series for real positive y. So one can actually study more generality by taking a complex number y with its real part positive, right? So, but what is this transformation? The transformation is showing us how far you can get to the modularity. You can't actually get the full modularity, in the sense you cannot have something where y goes into some constant upon y. That is what will actually correspond to a modular transformation. You can get such a series plus something else. So he says how the modularity is abstracted by means of an appearance of an extra integral. That's a principal value integral that he looks at. But still, this is one of the few results that are there when you are actually looking at 2k for at least k real. Okay. Now I would like to also talk about the work of Bruce Berndt. All this is developing the background for the results and the goals of our work. Okay, so Professor Berndt derived an important transformation formula for a very vast generalization of Eisenstein series. The Eisenstein series that I talked 5-10 minutes before, he vastly generalized them. As a special case of one of his results, one gets this beautiful result. You have z in the upper half plane, k is any integer, and you are actually looking at this particular formula. Now, see, what is the importance of this formula? If you are taking k to be 1 minus 2m, m can be any integer. So this k can be a positive odd integer or a negative odd integer, right? But when k is 1 minus 2m, you actually get the famous formula of Euler, which expresses zeta of 2m in terms of a rational multiple of the Bernoulli numbers of index 2m. Why is this very important? This is very important because the Bernoulli numbers are rational multiple of pi raised to 2m. Why is that important? Because if you have rational multiple of pi raised to 2m, that immediately gives you that the number is transcendental, because pi is transcendental. So if you take any power of pi, that is going to be transcendental. And if you are multiplying that by a rational number, again you are getting some transcendental number. So zeta of 2m becomes transcendental number for every n, every integer n. I mean positive integer n. So that's a very important result of Euler. But there is no corresponding result for Riemann zeta function at odd positive integers. Saying, are they transcendental? We don't know anything, except that we know that zeta of 3 is irrational. That was proved as late as 1979 by Roger Appéré, a French mathematician. You see, Euler's result, this particular one, is somewhere in 18th century, if I'm not wrong. And only in 1979 we are able to now get only one particular case, and that too not transcendental. We don't know whether zeta of 3 is transcendental. We only know that it is irrational. What about zeta 5, zeta 7, zeta 9, zeta 11, or any other higher values? We don't know anything. There are some partial results. A beautiful result of Zudelin, which says that at least one of zeta of 5, zeta of 7, zeta of 9, or zeta of 11 must be irrational. But we don't know exactly which. So Raman's figure is for odd zeta values, and that's why it is also quite important to study. So what is the nice thing about Bruce Berndt's result? On one side, when you put k equal to 1 minus 2m, you are getting Euler's result. Whereas when you put k equal to minus 2m, that means any even positive integer. You see, m is any non-zero integer here. So except m equal to 0 or k equal to 0, you are taking any even positive integer or negative integer. That gives us Ramanujan's formula for zeta 2m plus 1. So that's absolutely beautiful, because you get both results, both fundamental results just from a single formula. But if you consider the Lambert series here, when you are putting k equal to say minus 2m, okay, here what do you get? 1 plus 1. So you get something. I mean, that is what actually is giving us this formula. But when you look at k equal to 1 minus, when you look at k equal to minus 2m, then this is sigma minus 2m minus 1. And for that we have information, a lot of information. All of these I just discussed come into modular forms. But when k is 1 minus 2m, even though you are getting this particular formula of Euler, you don't get any information about this Lambert series itself, or this Lambert series. Because when you put k as minus 2m plus 1, this just becomes minus 1. 1 minus 1 is 0. So all this just gets wiped out. And from there you get this formula of Euler. So while you get the formula of Euler, you don't get any information about this particular Lambert series. Then this index here, k minus 1, is a even positive integer or even negative integer. So again, we have results, very few results, which actually can look at what sort of transformations one can get for Lambert series corresponding to this index k minus 1 being an even integer. Okay, that's the only result due to Green that I talked about. But for a equal to 0, we have a result due to Wiggert and Bellman, and that actually goes back even before to Wiggert in a different equivalent form. So I will actually express. Okay, I'll discuss this later. There is work of Wiggert, but right now you look at this a equal to 0. When you take 8 powers of all divisors of n and you take this sum, when a equal to 0, what are you doing? You are actually just counting how many divisors you have. So that's why you get this divisor function d of n. So you have this particular transformation. Why is it? What is this u function? This is the trichomy confluent hypergeometric function. This u is expressed as some sort of combination of this confluent hypergeometric function 1f1, which is defined in this way: summation n equal to 0 to infinity b sub n over c sub n z raised to n over n factorial. What is this b sub n? This is the shifted factorial or the Bookhammer symbol. So a sub n, for example, is defined as gamma of a plus n over gamma of a, gamma being the Euler gamma function. Why is this particular thing important? Why is it important to study this particular Lambert series? That will also build a case for studying our more general Lambert series, where instead of a equal to 0, you are taking a is any even integer, right? So an important problem in analytic number theory is to study this particular moment, the 2kth moment of the Riemann-Zeta function on the critical line, on the real part of s is equal to 1/2. So you know that the Riemann hypothesis, which is one of the most famous unsolved problems, states that or assumes that all of the complex zeros, complex roots of the Riemann-Zeta function zeta of s lie on the real part of s equal to 1/2. Okay, that has not been proved as of yet. So one of the instrumental problems towards making some progress in the Riemann hypothesis is to study these moments of the Riemann-Zeta function on the critical line. So critical line is real part of s equal to 1/2. Okay, and to find their asymptotic expansion, or to find what is it asymptotic to. So for example, L sub 2k of t is believed to be asymptotic to some constant depending on k times p times log t to the power k square. Unfortunately, that has been proved only for k equal to 1 and k equal to 2, and that too is something which goes very back in the past. So for example, for k equal to 1, this is due to Hardy and Littlewood back in 1916. For k equal to 2, this is due to Ingham, another British mathematician, who did it, I think, in 1930s. So how is the Lambert series connected with d of m, the divisor function, come into this particular study? So if I call this phi of z as this particular Lambert series minus gamma minus log z upon z, gamma is the Euler constant. So you see, this is what it is, right? Here I see this gamma minus log y upon y. So that is what I'm subtracting from here. Let's take this 1/4 on the other side. Okay. So this is my phi of z. Then what are people looking at? They're trying to again see whether you can get a modular transformation. Unfortunately, you cannot, because when you replace this z by 1/z, then you are getting the transformation of the form 1/z going into z, or z going into 1/z, but you are also left with some other function which is big O of x to the alpha. Big O is meaning that if you have f of x equal to big O of x to the alpha, then there exists a constant c and a number x naught, such that for all x greater than or equal to x naught, modulus of f of x is less than or equal to that c times x to the alpha. Now, by applying this particular formula, one can actually get to this particular result due to Atkinson. So you see, we are considering the k equal to 1. 2k was there, right? So k is equal to 1. So we are looking at the second moment of the Riemann-Zeta function on the critical line, and we are getting an asymptotic estimate for it. You see that t log t, okay? So we can see that this is T log asymptotic to T log T, as was given in the previous slide. So this T log T, and then you have certain. So this is actually the main term, and then E of T is the error term. But this formula is what is being used, and so that involves this particular Lambert series. Now, one also studies this smoothly weighted moment of the Riemann zeta function, wherein you actually put this e raised to minus delta t, okay, and you let delta tends to 0 plus. Okay, once you put this dampening factor, exponential decay is what is achieved, and so things become slightly simpler. But then you want to let delta tends to 0 plus from outside. Okay, so and look at the asymptotic estimate. So for k equal to 1, there is a formula for L2 of delta, which consists of the main term plus error term, and you can also write it as an asymptotic series, but it is not a convergent asymptotic series as delta tends to 0. But in a very recent work by Bettin and Conte, it's in 2013, they actually studied the same series that we have studied. All the results are, of course, completely different. But the thing is, what they are doing is that for this particular series, they are obtaining number of results of this kind. They first show that this can be analytically continued to the complex plane, the slit complex plane, as well as they get as an application of the result an exact formula for the second moment of the Riemann zeta function. And this formula gives them an asymptotic series which is convergent as delta tends to 0. You see, previously as delta tends to 0 plus, we were getting an asymptotic series but which was not convergent. But here you are actually going to get a convergent asymptotic series. They also got a simple proof of the organized function formula as one of the results. So what is our objective? Again, even though they consider the same series that we are considering in the same level of generality, they are not able to obtain, or at least in the papers, is not the explicit transformation that is given for this series. You always have such a series expressed in terms of another series of the same time plus either some Bigot expression, or you have some complicated contour integral or some principal value integral, because of which you are not able to get an explicit transformation. So that is where we actually want to fill the gap and obtain an explicit transformation. So you see, we want a transformation wherein on one side you will have this particular series, on the other side again you will have sigmas of A of n, but another function, and you will not have any other contour integral left as it is, or you estimate that. So such a thing is quite useful, especially in the context of Voronoi summation formulas, because when you do not have, when you have the error term expressed as infinite series of, let's say, Bessel type functions, then actually you can estimate them in a nicer way and try to improve the bounds, and that is what is traditionally done. So such a formula, as explicit as one can get, is always welcome. And what we do is we first get this formula for any y. Again, y is always going to be with the real part of y greater than 0. And here, when I look at e raised to 2 pi I n z, I'm always going to take that with imaginary part of z greater than 0. So it's in the upper half plane. So both are equivalent. So I'm going to do that first for any complex race at real part of a greater than -1, and then for real part of a greater than -2 and -3. So I take it into the to the left of imaginary axis as much as I want. I can do that. Of course, I cannot take it up to -infinity, but you can take your n as high as possible, and still that will be you'll be able to get a transformation for this explicitly. Then, as corollaries, we not only obtain the well-known results from the theory of modular forms, because we can put a to be any odd integer. You can put a equal to 0, which is already studied, but we can also get new transformation when a is an even integer. Okay, so if we before looking at the results, let me actually go over this generalized hypergeometric series PFQ, which is defined by, you have p parameters in the top, q parameters in the bottom, and the argument is z, and this is the infinite series. So you have all these Pochhammer symbols consisting of quotients of gamma functions, and then z raised to n over n factorial. Okay, so this series converges absolutely for all z when p is less than or equal to q, but when p is equal to q plus 1, it converges only in the interior of the unit disk, and it diverges for all z not equal to 0 if P is greater than Q plus 1 if the series does not terminate. So this is well-known fact from the theory of hypergeometric series that we are going to assume. So the nice thing is that if you are, say, using 1f1, which is what I will be 1f1 or 1f2, these are the only two functions which we will be making use of. So that falls into this first category. 1f1 falls in this category because P is 1, Q is 1. So it is convergent absolutely for all Z. Okay, and uniformly for all compact subsets of the complex plane. And if you have P is equal to Q plus 1, that is something which I don't think comes into our use. We have only 1f1 and 1f2. So the convergence is always absolute. That's a nice thing. Okay, this Pochhammer symbol, which is the quotient of gamma functions, is essentially this. I mean, it is equal to this finite product A times A plus 1 so on up to A plus n minus 1. Before I go over the main results, let me also look at the definitions of Bessel functions. There are two Bessel functions, one of the first kind and one of the second kind. These are their definitions. This is essentially 0f1. So you see that y is expressed in terms of J Bessel function. Okay, and when this is for nu not being an integer, but when nu is an integer, you take the limit, and then that becomes y sub n of z. There are also modified Bessel functions. This is the modified Bessel function of the first kind expressed in terms of J, and there is modified Bessel function of the second kind which is expressed in terms of I. So you see everything is expressed in terms of J. Okay, this is what is going to be the very important function for our work. Okay, I would like to say about two important results that we use heavily, or actually in a generalized manner in our work. One is due to this Russian mathematician Koshlikov. So what is he saying? If you take this particular combination of the Bessel functions, so you have the Bessel function of the first kind, and you have Bessel function of the second kind, as well as Bessel function, modified Bessel function of the second kind. So you have 3 of the 4 Bessel functions in this particular function. I call this as Koshlikov kernel, and what do I look at is the integral transform with this being the kernel. Okay, and what do you see? You see that the K Bessel function is actually self-reciprocal in this particular Koshlikov kernel, or in this Koshlikov transform. That's a very beautiful result. This result is analogous to the Laplace's result that exponential function, when integrated against cosine, gives back exponential function. Why do I say this is analogous to that? Because if you look at exponential function e raised to minus x, it can be written as inverse Mellin transform of gamma function, and K Bessel function is nothing but the inverse Mellin transform of square of gamma function. Okay, essentially. So this identity is valid for any complex nu such that its real part is between minus half and half. This particular kernel is very important because it appears in Voronoi summation formula. Voronoi summation formula is something of this form, a formula for summation n equal to 1 to infinity a of n times f of n, where a is arithmetic function, f is a sufficiently smooth function. Koshlikov in the same paper also generalized the modified Bessel function. Although he doesn't write it explicitly, this is what is the generalization, because let's say we put mu equal to minus nu. This is gone, right? This becomes 1. And you are left with only k sub minus nu of t times this kernel. See, this kernel is same as what appeared in the previous slide. But this k sub minus nu of t is same as k sub nu of t, because the modified Bessel function of the second kind is an even function of its order. So you get back the same integral that I had on the previous slide here. And what does that evaluate to? It evaluates to this k nu of x. So on this right hand side, when you put mu equal to minus nu, you must get k nu of x. So in other words, for general mu, you are actually getting a generalization, one variable generalization of the modified Bessel function. Okay. So what we did was, in our work, we also required a further generalization of the modified Bessel function. So this is having one more parameter, w, and it's not just for the sake of generalizing that we are considering such a thing, increasing parameters. This appears very naturally in our work, and its inverse Mellin transform representation is really very simple. 2 gamma quotients in the top, 2 in the bottom. Okay, so here are some conditions. I won't go into the details as to why one requires them, but in order to have the function analytic and well defined, one needs all these conditions. So when you put nu equal to 0, you have to actually take in the limiting case. I mean, you cannot just put nu equal to 0, because you will see you have a problem, because here you'll have 0, and all of this becomes also 0. This difference becomes 0. So you have 0 over 0 when nu equal to 0. So you have to take the limiting case. But when w equal to 0, we get the Koshlikov's generalization on the previous slide that I showed you. And when we keep w as it is, but put mu equal to minus nu, we are getting nothing but some power of z times the k nu of z. Okay, so here's our main result. So you have this explicit transformation between this Lambert series going into another series. Although its summands are slightly more complicated, it consists of this sigmas of a of n and just that's it. Some residual terms. You don't have any BO term, or you don't have anything consisting of complicated contour integral. This right hand side can be expressed in terms of this generalized modified Bessel function that I introduced on the previous slide with w equal to 0. So it's at the level of Koshlikov's generalization. Okay, we don't really require for general w until the end of my talk. Okay, so this is for real A greater than -1, but we can analytically continue it for real A greater than -2 and -3, where n is any non-negative integer. And while I won't go into the details of how one obtains an analytic continuation, I'll just briefly tell that whatever expression you have, you look at its asymptotic expansion, or at least asymptotic estimate that one has, and subtract terms, add and subtract terms, and then again, when one does this process, one has to assume first of all real part of a greater than -1 only, and you take out some terms from its asymptotic estimate or asymptotic expansion if you have one. So for example, here I have taken this a sub m times this constant, right? This has m plus 1 terms, right? Those m plus 1 terms I'm subtracting from the asymptotic expansion or asymptotic estimate from this function, and I'm adding and subtracting those. But now you look at the identity and you see whether this is analytic for a more general region than real A greater than -1. And if that, on this side also, if you are having analytic, then you can use the principle of analytic continuation and you can get to the extended region. That's what is the thing. So here is the outline of the proof. I mean, the main, by the way, this is what we call as master identity. The reason we call this as a master identity is that for special values of A, it gives all of the well-known results as well as new results as special cases. From one single identity, you are able to get a lot of information. So how does our proof of the previous case, let's forget about the analytic continuation for time being, and let's look at the simpler one for real A greater than -1. And let us actually see how the outline goes. So one has Koshlikov's result that I showed you a few slides back. That is instrumental. We put mu equal to half, so that gets us this exponential, and for that we simplify this and we get this. And you see, this is what appeared in the summand essentially. There was a 1f2, there was a cosine hyperbole. Okay, and then we use a version of Voronoi summation formula. So the Voronoi summation formula that we are using is due to, I mean, this version is due to Andrew Guinan, and this is a beautiful symmetric version. What does it say? If you have A as a complex number with its real part between -half and half, and if you have F satisfying these conditions, so I'll explain what do we mean by F or something being an integral, but F has to tend to 0 as x tends to infinity, and this F, x f prime and x square f double prime, they should be in L2 on 0, infinity. Then if you have G to be the Koshlikov transform of F, then you have this symmetric formula. Okay, so what is the symmetric formula? I mean, you take the left hand side, just replace F everywhere by G. Now, why do we use Guinan's version and not the usual well-known version of Voronoi summation formula for sigma function? Is because the conditions there are a lot more difficult to verify than the conditions here. Okay, so one has to really look at functions of bounded variation, and there are a number of versions actually. So if you want to use a particular version, one has to really look at what all conditions one has to verify. Although for our own transformation, we are going to take f to be exponential function e raised to minus ny. So there you have exponential decay, and so a function in a Schwarz class would be what one would need. So one can use that version also. But in the process of using this particular version, we are actually going to get some nice integrals also, new integral evaluations. So this version is also useful to work with. So what do I mean by this f being an integral that I do here for f as well as f prime? By f being an integral, I mean f can be written in this form: integral from a to x h of t dt for some function h and some a between minus infinity and x. So we first prove our result for real a between 0 and half and y greater than 0, and then extend it by analytic continuation to complex a such that real a greater than minus 1 and complex y such that the real parts are positive. So as I said, I take my f to be e raised to minus xy times x to the a by 2. See, this is the same thing that appeared here. Okay, just put instead of t, x. Okay, so that, and its transform is what I need, right? If I want to use f as that e raised to minus xy times x to the a by 2, I need to calculate g in order to get this formula as explicit as possible. And that is given by Koshlikov already. So I know what the right hand side is. So I know what g is explicitly. So these two sides are already known. However, I need to evaluate these four integrals. And while two of them are very easy to do, you take f being e raised to minus xy times x to the a by 2. So this becomes essentially gamma function. And this other one is also easily reduced to 1 upon y. However, the other two require some work, and one of which nicely evaluates to 0. It's important because otherwise the formula would have been really very complicated. But very nicely that becomes just 0. Okay, and this other one is what actually appears in the residual terms in the main formula. So see, using some reflection formula for gamma function and all, you can actually convert it in this form. So this is what I get, and from the definition of mu k nu of z comma w, which I showed you as our generalized modified Bessel function, you can write this in this compact form. But now we have obtained it for real a between 0 and 1 half only. Now let us keep y greater than 0, but now let us try to extend this analytically as a function of complex variable a to a maximum possible region. And for that, I need to know the behavior of this function as n tends to infinity. That actually turns out to be big O of this. And along with this, see, you have this particular one and you have this particular one. From here, you know it is big O of this quantity. For this, you can easily see by an elementary argument, it is big O of n to the 1/2 times mod real part of a plus epsilon. So when you combine the two, you actually see that the right hand side converges uniformly for real a greater than minus 1. What about the left hand side? Oh, left hand side is analytic for any complex a. You have this exponential decay here. What about all these functions? I mean, there also you have to see. Only the problematic thing would be, let's say, for example, if I consider zeta of 1 minus a, then a equal to 0. Would that pose a problem? Apparently it looks, because the Riemann zeta function has a pole at s is equal to 1 or a is equal to 0 here. But it gets removed, okay? Because when you put a equal to 0, secant 0 also has a pole. So when you combine the two, you can actually remove that apparent discontinuity or apparent singularity. Sorry, not discontinuity. So in essence, what one can get is that because this is analytic for real part of a greater than minus 1, and because this series converges uniformly for real part of a greater than minus 1, you can appeal to Weierstrass's theorem on analytic functions. It says that if you have a uniformly convergent sequence of analytic, uniformly convergent series of analytic functions, then it must be analytic itself. So this becomes analytic. All of that is analytic for real a greater than minus 1. This is analytic actually for every complex a. So in particular for real a greater than minus 1. So both sides are analytic for real a greater than minus 1, and 0 less than a less than half falls in there. So by principle of analytic continuation, this result holds for really greater than -1. Okay. To further analytically continue it, as I said, one needs the asymptotic estimate at least for this mu k nu z comma w, our generalized modified Bessel function, and this is something that we obtain. Okay, so when I actually subtract the first m+1 terms, as you can see, I had subtracted this constant times am from here. Why didn't I subtract this b sub m as well? Because when you put, let's say, a equal to 1/2. In our case, a was 1/2. Sorry, mu was 1/2 and w was 0. So when I put mu as 1/2 and w as 0, you get simply gamma of minus k. Gamma of minus k is infinity. So 1 upon gamma of minus k is 0. So everything just vanishes to 0. This is b sub m. So you essentially have to only subtract this part. Okay. So I'll just briefly say you analytically continue that by subtracting these m+1 terms from the asymptotic estimate and compensate that by adding also. So you have to actually look at this particular series. But again, you appeal to the fact that now both sides are analytically analytic in real part of a greater than -2 and -3, and uniformly conversion in real part of a greater than or equal to -2 and -3 plus epsilon for any epsilon. So you again appeal to Weierstrass's theorem of analytic functions. Okay, yeah. So let's just skip the details, but now let us move on to these new transformations that we get first. I'll then explain how the old transformations you will get. So I'm looking at A being 2m. You see, we are transforming this series into a corresponding series which again has sigma sub 2m. It has a bunch of residual terms, and then you have this particular complicated looking segment. What are these functions? We know sine hyperbolic, cosine hyperbolic. This finite sum also one is able to, it just consists of factorial. What are these two functions? This is called as sine hyperbolic integral and cosine hyperbolic integral, and they are two special functions which are well studied. They are also appearing in NIST, this National Bureau of Standards, the one that is there in US. Sorry, NIST Institute. So this hyperbolic sine integral is defined as integral from 0 to z of sine hyperbolic t upon t dt, and this cos hyperbolic integral is defined as gamma. Again, gamma is Euler's constant plus log z plus integral 0 to z cosine hyperbolic t minus 1 upon t. Okay. Now you may say that, okay, you have obtained some transformation, but of what good it is, or how is it really important? Why should one look at a few slides between the series that we got for a equal to 2m and the original, I mean, the well-known series when a is an odd integer. So when a is an odd integer, what you see is exactly a similar type of sum, some similar type of series. Of course, if I take, let's say, m is less than or equal to 0, then this term is empty. This expression is empty. But you see sine hyperbolic here and cosine hyperbolic here. Okay, you have these additional functions when a is an even integer, but not when a is an odd integer. But when a is an odd integer, then this just very nicely simplifies to exponential function again. So you get this modular transformation with exponential minus n times y going into exponential minus n times some constant upon y, which is a modular transformation. But in a, even you don't get modularity, but still you can see the same exponent 4 pi square n by y is what is appearing in the arguments of all of these functions. Even here it's 4 pi square n by y. So it's very nice to see this connection. So where can this be useful? So you have this particular series expressed in terms of this one. Now if you want to understand asymptotic behavior of the series as y tends to 0, of course if you put y equal to 0, the series is not going to be converging, right? But when you like y tends to 0 plus, you can actually make use of a transformation that we have obtained here in order to get to the asymptotic behavior of the series, and from there we can actually use them in applications in the case of, let's say, Riemann zeta function theory. I mean, there you actually can do it even for any complex A, because we have a general transformation for limit replaced by any complex number A. Okay, so let me skip this proof, but let me see that along the way we need some results which we could not find in the literature. For example, in standard tables of this Prudnikov, Brichkov, or Marichev, the Russian authors. There are some number of books. We weren't able to find such results, so we derived them ourselves. But one thing that is really a nice outcome is that when you put A as -2m minus 1 in our result, we get the famous formula of Ramanujan as a special case. So it becomes a corollary of our result. And not only that, when we put then A equal to -2m, see here you had n to the A, right? When you put A equal to -2m, you actually get a companion to Ramanujan's formula. How is the connection? You see on the left hand side I have 1/2 zeta 2m plus 1 plus this series where I have -2m minus 1 as the exponent of n. The denominator is the exponent to 2n alpha minus 1. You have the similar thing here, only that 2m plus 1 is replaced by 2m. Okay, and
sir, is your net proper? I think there is some connectivity problem again.
Oh,
yeah. Okay. I think now it's okay.
Okay, thank you.
Participants, is it okay now?
Yeah, I'm sorry for the problem. Can I start?
Yeah, sir. You can continue. No problem.
Okay, sure. So you can see the nice companion to this formula of Ramanujan that one gets for even zeta values. Now, of course, these are expressible in terms of rational multiples of pi to the 2m. One has an explicit formula for those. But what this is actually giving you is this Lambert series is expressible in terms of what are called as Herglotz type functions. I won't go into those, but here is this psi is the logarithmic derivative of gamma function. Okay. This formula itself is not available in the literature. It is new. There are analogous results, but you see, let me compare and tell you why one doesn't get our formula, although they are doing it in much more generality. So here is one result due to David Bradley, where you see he's considering L, the L function, which is defined as summation g of n over n to the s. G of n is a periodic function. Okay, so because this is a periodic function, it actually this L series converges in real part of s greater than 1. So if I take, for example, g to be identically equal to 1, then it will give me the Riemann zeta function. Okay, and then it will be zeta of 2m only, but this will be 1, and then you have n to the minus 2m. So that is it not giving us this exact formula that I'm claiming is new? The answer is no, because here if you see, the condition is g is an odd function of. So odd periodic function. So you cannot take.
Sir, your video is not visible. Your video is not visible.
Oh, okay. Okay, but screen is.
Yeah, screen is visible. Screen is having no problem.
Okay. Let me see.
Yeah, it's okay. You can continue, sir. No problem.
Okay.
You can continue. No problem. Okay, it's okay. You can continue.
Yeah. So one actually cannot put g identically equal to 1, because when g is odd, one doesn't get g identically equal to 1 because it's an even periodic function. One can actually have a corresponding result, but when you put g identically equal to 1, you are getting back Ramanujan's result. So the companion formula doesn't come from any of these results of Bradley or due to some results by Professor Berndt also, because in all of these cases, one has the even zeta values appearing for g being an odd function, so you cannot put g identically equal to 1. Anyway, so first we get it in this form, and later on, in order to get to that final result that I showed in companion to Ramanujan's formula, one has to use one of the recent results that I obtained in my joint work with Rajat Gupta, Rahul Kumar, and Vivekananda Manji. Why is this result special? Because you see, this particular integral is conditionally convergent, and you are taking infinite sum of that conditionally convergent integral, and yet you are able to get it in the closed form. You of course cannot take the order of integration and summation. It will lead to a divergent integral. Okay, so this result itself requires a lot of work to prove, but this is proved in another paper of ours, which is very fruitful in this work as well. Okay, let me go back to some more two more special cases that I'll very briefly discuss. So when we take a tending to 1, a is any complex number in our case, right? You have n to the a upon e raised to ny minus 1. Y I'm taking as 2 alpha, and then I'm taking alpha beta is pi square. Okay, so when you let a tend to 1, you actually get this transformation formula for E2. E2 is the quasi-modular form. Why is it quasi-modular form? Because if it were a modular form, this term would have been absent, but this is not absent. Okay. So let me skip the proof. But when a is equal to minus 1, one gets this nice result, which again is connected with transformation formula for the log of Dirac-and eta function. Here is the Dirac-and eta function. It satisfies something like eta of minus 1 by z, the square root of minus I z and eta of z. Okay. This a equal to 0 case leading to d of n. This is something that I said. It has an equivalent form which we thought was a new one until a few days back when we found out in a paper of Vigard. So this formula is unfortunately not our result; it's already due to Vigard. And but again, this is a very nice result, and Vigard gives the asymptotic expansion of this Lambert series as y tends to 0. Okay. So the series here converges because you actually, if you look at the asymptotic expansion of psi of z, you will see that this summand is big O of 1 by n square. So it's actually absolutely convergent. Okay, in the remaining maybe 10 minutes, what I will do is I will explain some things coming from theory of integral transforms which are important in our work. So I discussed earlier at least one of the two kernels of Koch-Lekar. So this was the kernel that I looked at, and there is a corresponding one where if you see the difference is only that m is replaced by L, and what is the difference between m and L? Here it's plus 2 by pi, and here it's minus 2 by pi. Okay, so of course this order is you have to also multiply by minus sign, but essentially one can see the similarity between the two kernels. These two kernels actually, yeah, I'm sorry, yeah. So these two kernels come as special cases of this more general kernel involving hypergeometric 0f3 functions. Okay, so this 0f3 is a special case in turn of 0fn, which is called as hyper-Bessel function, whose theory was initiated by this mathematician, I think from Bulgaria, called Deleriu. So, or French mathematician, I'm not sure. But these hyper-Bessel functions have a lot of applications. Okay, so one can actually get this kernel giving us the previous two kernels as special cases when w equal to 0 and 1 respectively. Okay, again when you see nu is equal to 0, we have 0 over 0 form. Okay, so it has a removable singularity. I won't go into the details, but otherwise it has pole at every non-zero integer. So one has to be really careful while taking, let's say, g sub 2, it doesn't exist. Now, a thing that I need to say is that this kernel is not new. In fact, it was studied by G.N. Watson. He studied it in the form of this particular integral. Okay, and we have this equivalent relation between the two. But it is only holding when this is the condition for the parameters. So many people, in fact, many Indian mathematicians, Bhatnagar, Olkha, Rathi, Dahiya, also one of the speakers in this session of ours, Professor Pathan, they have worked on more general kernels which encompass this function. However, nobody had studied the importance of this kernel from the point of view of number theory, and that's what we have, I hope to have demonstrated in this work. So, for example, when I put nu equal to 1/2, then this turns out to be the Hankel kernel, right? I mean, if you look at the Hankel transform of a function, that consists of this J Bessel function. Also, as I said before, when I put w equal to 0 and 1, you get the two kernels of Koch-Lekar as special cases. They are of prime importance in number theory. I don't have time to go into the details, but they are very, very much important in number theory. So we generalize this formula of Koch-Lekar, and what it gives is that in this generalized Koch-Lekar kernel, or let us call this as a Watson kernel because Watson studied it for the first time. This function, when integrated against this Watson kernel, gives you this function that enabled us to define our generalized modified Bessel function. In fact, that was it. And when you put mu equal to minus mu, it gives you a nice self-reciprocal function. T to the w k nu of t, when integrated against this Watson kernel, gives you again x to the w k nu of x. So it's self-reciprocal. An application of result, this result, when nu is half, is for this obtaining this transformation involving this Rk of n function. So what is this Rk of n? Sum of squares function. So what is this meaning? You take the number of representations of a positive number n as sum of k squares, and the signs and different orders will give distinct representations. For example, if I take n equal to 5, how many ways there are 5 to write as sum of 2 squares? Here k is 2, right? So sum of 2 squares. Or you can write as 2 square plus 1 square, or 1 square plus 2 square, or minus 2 square plus 1 square, and so on. So in all there are 8 representations. Okay, so if I take that Rk of n function, then we get a nice transformation for that, which involves again our generalized modified Bessel function, this time not with w equal to 0, but w being k over 4, where k is an integer greater than or equal to 2. Okay, this in turn can be derived, and I won't go into the proof at all, but as a special case, this gives this modular transformation. Okay, so every time we are getting more general transformations, where in special cases you are getting modular ones, and so the more generality allows you to get non-modular transformations as well. Okay, so just an outline of the proof. Here we use the version of the Voronoi summation formula for Rk of n that we rigorously formulated. So it was already given by a Russian mathematician Popov and Guinand, but the conditions were missing, and one has to really verify a lot of conditions, but one does get a symmetric form after that. So let me say in my last slide, are there any direct proofs of the transformations, the new transformations that we get as special case of our master identity? In fact, when A is equal to 2m, can we obtain them in a direct way? This generalization of modified Bessel function that we studied, we only obtained those properties of this function that we needed for getting our general transformation. But this seems to be worthy of merit and demands further study. For a study by itself, I mean, just for the sake of this studying this function, I think that will also be quite fruitful and lead us to various applications. We are also looking at the application of our transformations in the theory of Riemann zeta function. This is a joint work in preparation. And my last slide is that are the applications of such a result, which is the A equal to 0 case, in transcendental number theory. For example, Paul Erdős has showed that if you take this series d of n q to the minus n for any integer q with mod q greater than or equal to 2, it is irrational. So for example, if I take y equal to log 2 in this formula, that will give me an irrational number on the left. But what can I get from the right? I mean, can I even get some sort of result which is important from the point of view of transcendental number theory? That is another question that one can ask. So we have further results of the same kind. So here, instead of 1 upon e raised to n y minus 1, we have n raised to minus 2 upon e raised to n y minus 1. That involves zeta of 3, for which you know zeta of 3 is irrational. Okay, so can that be used again in transcendental number theory in some way? I'm just throwing out questions. I don't have any insights as of now on these problems, but just some food for thought for all of us. With that, I will stop here. I would again like to thank Dr. Dilip Kumar, Dr. Suresh Singh, and all of the people in University of Kerala for giving me an opportunity to give a talk here. Thank you very much.